Gotcha.
Yeah, and I think this is a really complex conversation, and we cannot cover every nuance here. Yeah, because this can get very hairy. There a few, but just a couple quick talking points on that because I think this is highly critical. Be considerate of when your soil resistivity testing was done, and then what changes were made to the site. Why do I say that? Because I've run into this many, many times now. We did a soil resistivity test on XYZ date, and it was a green field, right? It was all native soil, and maybe it rained yesterday, whatever the rainfall conditions were. But we removed that native soil, we backfilled with a new material, and now our resistance is completely different than what was calculated, right? Very well-meaning engineers have made this mistake many, many times, right? It could be high voltage, it could be a substation, it could be a communication site, it could be whatever, right? We backfilled for structural reasons, and we introduced, let's say, an aggregate, and that aggregate brings in, especially when freshly laid, and freshly here could be up to, maybe a year or more, it's going to be porous. The soil is very porous. It has an air gap, and we use air as an insulator all the time. It's not great for making that connection to the rest of the earth that's around it. So we want to be considerate of that. Next thing is, and I'll end it here, is going to be the test instrument, right? An instrument of this caliper, like this 6472, I get probe resistances with this, right? I get errors that will be produced. I'll get a greater than, a less than symbol. Sometimes I can even produce both. And what that's telling me is, yes, I produced a value. Yes, there's a value being displayed here. However, it doesn't meet the specification for accuracy. What is the instrument doing? It's sampling, right? There's an AC test current flowing between those 2 points, pushing and pulling. It's taking samples of that measurement as that test current is being transmitted through the earth. By doing that, I can then compare those samples and say, hey, this is a problem because my sampling is very different. The deviation between these measurements is too great to call this accurate. So when we can get this, especially in high resistance soils where, like Tom mentioned, there was a gravel road that was laid, or I disturbed the soil at this site to accomplish whatever, usually some type of structural change or structural addition that needs to be made to support whatever is being constructed. We put our ground electrodes in that disturbed soil, and my probes then, which are electrodes, are placed in the earth in also disturbed soil. Now they have a high resistance. Benefit to fall potential and fall potential variance like slope and intersecting curves. The probe resistance can be an order of magnitude substantially higher in resistance than the electrode that is under test, but there is a threshold there. It can't be a 5 ohm system in a 10,000 ohm probe. We're not going to get a good test setup. Buy an instrument. If you're doing these types of measurements pretty consistently, buy an instrument that gives you those values, because now I can troubleshoot what the problem is with the measurement. Maybe I'm testing to the northwest, and the northwest is in a direction in which an aggregate plant is, right? And they have a lot of waste that's poured over, or a recent experience I had, there's a trash dump this direction, and they laid a membrane down, right? Now they've abandoned it since, it's no longer in operation, but that membrane is causing me to have very, very high resistance soil, and I'm not able to perform my test. Now I'm going to test this way. What else is going to be valuable there is I need to put that on the report. My test probes were laid out this direction. I like the idea of giving a test report that not only gives me all the values and the conditions, but it's just a simple map that of the direction in which I tested, where I made the connection to the electrode system, and so on and so forth. The more data, the better there. It's a CYA thing there. Tom mentioned rainfall, right? I like your idea of waiting to make sure that we're in that Goldilocks zone of it rained, but not too recently and not too long ago. Notate the last rainfall. Google is your best friend on some type of data point like that, right? Also consider how much rain fell. If I'm forced to do a test today and it rained yesterday, but what does that mean? Did it sprinkle yesterday, or did it pour rain for 6 hours? So we want to be considerate of everything that can have an effect on a resistance measurement. that is introduced into the soil and around those electrodes. Overall, we observe frost lines for that for many reasons, but that could be one of those reasons. We go from 32 degrees water to 32 degrees solid frozen ice. We see a resistance change that could be 3 times what the resistance is at 32 degrees liquid. So we can see all sorts of things that'll change there. That's why I like the inter-season testing perspective, because I build a profile, right? I'm going to give you the last thing, and I harp on this big time in seminars and to anyone that I talk to about this subject. But let's be ethical in how we do our tests. What do I mean by that? Now, in your scenario with NITA testing, you're giving these results into a customer. This may apply to maybe an alternative test. Maybe I'm doing a test for someone that doesn't have a great understanding of what these values are. Or it's a CYA thing on my part. My threshold for what's good, what's bad is 5 ohms. Let's say I go and I do a test and it's 4.8 ohms. Let's be considerate of accuracy, right? Not so great in ground resistance testing. I repeat the measurement, whether it's taking multiple follow potential measurements on my traverse to H, or I turn that test and do another follow potential measurement and I get values that are very similar. Let's say it's 4.8 ohms. My threshold's 5 ohms, right? I'm going to put an asterisk on that. I want to be considerate of all those all those conditions that I'm in. Maybe it's April and it's unseasonably wet. What's the resistance going to be in July when it's unseasonably dry? So we want to be considerate of the value and making sure that there's headroom on that value given the environment, given the scenario. So be aware that just because you have a threshold and you've met it doesn't mean that it should necessarily pass in that particular case, right? And that could be applied to any type of electrical testing or anything in life, of course. But, the same could be true with insulation testing as well, or low resistance testing.
I want to say 2 things real quick. One is going to be...
We're going to just keep doing this.
Keep it going, baby. Keep it going.
A lot of people are like, what should my number be? Right, when you're doing resistance testing. Yeah. And I'm going to give you the quick dirty 3 answers. Okay, so depending on whether you're looking at the NEC or the NESC or the IEEE, right? It depends. So a normal residential is going to be 25 ohms or less. Okay, so that's typical normal. I see your shrug. Normal, typical residential, maybe even commercial. Okay. Industrial is going to be anywhere from 25 ohms or less to 5 ohms or less. And then when you start talking about substation, even some distribution substations might be 5 ohms or less, right? Mm-hmm. But if you're talking about transmission or generation, then we're talking about the big boys here. Those are going to be 1 ohm or less almost every single time. So depending on your specific requirement and what your engineer also requires, you're getting paid by them, right? So that's ultimately what matters. But where do they pull these numbers from? That's where they get them from. So those are usually the 3 general numbers that you might see. And I've seen some customers say they need to be 8 ohms or less. I was like, I don't know where you get that number from, but fine. We'll roll with that. But I just want you to know that that's where they come from, the IEEE, the NESC, and the NEC. All 3 of those are generally the three major ones. That was the first thing. The other thing I wanted to point out was I want to use 2 scenarios, right? I had a customer, I didn't have a customer, but there's a customer in the past I was working with, and they had a solar field, and a really big solar field, and they had lots of inverters out on strings. You got to think these solar fields are huge, right? They're big sites. And so each one of those systems is it's a grounded frame essentially, and it's got grounding wire running under it. And they're like, this is already built. We want to test the grid resistance. I'm like, how the hell do you want to do that? So they wanted to go ahead and they wanted to get some. There are some proprietary special meters out there that you can get, like Duval, Hood, Patterson, and Duval, I believe is one of them. And they have some specialty meters out there. Are they good? As far as I know, yes. The guy that did that, that created that company, also co-founded and wrote IEEE 81 with the original author, I believe. So are they great meters? Yes, but I'm going to caveat that with yes. But those types of meters require very specialized software and training in order to perform the assessments properly. So if you're going to do that, make sure that you do your research. The other scenario I'm going to lean on is know your system what is the intent of grounding? Like we said earlier, right? You've got your resistance to earth and then the integrity of your grid. That's really the two things that you have. And know what test you're testing and which one of those you're testing. So we had a customer here locally. They're like, hey, we're downtown. We need to test our ground grid. I was like, okay, well, what are you trying to do? We're trying to check resistance to earth. I was like, dude, you got gas lines, water pipes, everything. You got a customer 10 feet next door. There's no way you're going to get this. He's like, well, how do I know what my ground resistance is? I was like, just go from your main panel to the utility pole. And if you've got 0 ohms with a point-to-point check or 1 ohm or less, then you essentially are on an infinite grid. There's no check that you can do. Right. So know your limitations, understand the intent of the test. And at that point, he was like, look, I'm trying to check something that I already know is perfect. So at that point, you're not going to have step and touch potential in the backyard. It's not possible because you're on the infinite grid with water pipes all around you. So just understand the concepts of what you are testing and how to apply those tests.